So, let's add in some blanks. The direction that a wire is forced through a magnetic field is up. Is that right? The direction that a wire that's not what's happening here. This is a coil that's being pushed down. Look at that. It says that it's pushing the coil down. I had a doubt there. But because the induced magnetic field around induced B field around a wire opposes the B field outside, this means that the wire's motion will experience a force opposing its motion. So it actually turns out that if I try to drop a current carrying loop down over a North Pole, it'll be slowed down a little bit because that north that's been induced is going to resist that north that it's approaching. But as a consequence, as it gets slowed down, the current's going to get driven through that coil. Now, I want to think about, oh, by the way, this is something that can be used as a braking system. It turns out that if you take a pipe, if you take a copper pipes are really good conductors. We know that about copper pipes. If you drop a North Pole into a copper pipe, there's a south up here, would you believe that North Pole going into the copper pipe, forget about solenoids for a minute, isn't this like an infinite coil solenoid if it's like a solid copper pipe? They've all been welded together, right? And if we don't let the electricity get out, like there's no leads on this copper pipe, if I shove that north in, isn't that going to mean that the top of the pipe is north and the bottom is south, kind of? Or I could think of there as being a million billion north-souths all the way along. Infinite coils, right? Infinite thin coils. Well, that means if I shove this north in, then according to my right-hand rule, current's going to go into the page on this side, and it's going to come out of the page on this side. But if there's a million billion wires here, because it's actually just one solid copper pipe, doesn't that mean that north, if I drop the magnet in, is going to experience resistant north poles the whole way as it falls down the pipe? We'll do this later. I got a copper pipe in my closet. It's true. I'm not just saying that to sound fancy. But there is a copper pipe hiding in the closet in this classroom, and I have a magnet. I want to see what happens if I drop that magnet into a copper pipe. What do you guys think is going to happen? Make your predictions, okay? Don't say it out loud or anything. You don't have to. Share it with a friend. I don't know. I'm just saying. You can say it out loud. I got some people with opinions, okay? I'm telling you right now, I mentioned the word braking system earlier. Something to think about, okay? All right, so we'll come back to that. Now, as I look at this, I got right-hand rule number 3 compared to what we've been calling Lenz's law. And you can look up the personal history on Mr. Lenz. I'm not going to do a historical aside on him right now. But the right-hand rule says if we have a current, I'll do my current in red, and that's going to be my input. Then when I have that input, I'll end up having an output of a force. If that input, that current, flows through the magnetic field that's shown here. Lenz's law says that if my input, I'll do my input in red, is this way, I'm pushing my wire through a magnetic field. Notice that this textbook illustrator wrote V for velocity. I'm going to say that we're pushing it. So we have a force that's going this way. Yep. If I force it this way, what's that? Oh, yeah. So if I push it this way, then the output, the current, ends up going this way. And people say, okay, so how does that work with a right-hand rule, left-hand rule? Well, you can see that this person here, that was the artist here, they were determined. They were going to have right-hand rule number 4. And if, like this artist, you're determined to have a 4th right-hand rule, then what you would do is you'd use your thumb as the direction of the force, your fingers as the direction of the magnetic field, and your palm would just push that current along. Okay? So if you're determined to have a 4th right-hand rule, you totally can. But if, like me, you like sort of the comfort of having one left-hand rule, because that left hand, it hasn't been doing much. Okay? And if you have to have a left-hand rule, this is the time to use it. Because a left-hand rule would have a magnetic field that's orienting this way. There would be an applied force. I'll make it be red because we were making our action be red. And the consequence would be a current going this way. And you check with my artistry there. Is that a left hand? Yeah, okay. Don't get mixed up. You use your right hand when you're trying to induce a current. You'll mess it up. Don't do that, okay? And if you're somebody who doesn't know how to tell their lefts from their rights, there are lots of strategies. I'm going to tell you right now, if you walk into one of my tests and you have that written on your left hand, I won't judge you, okay? What's that? The letter L on your left hand, I won't judge, okay? If at the end of the day, that's how you cheat on a physics test, that's the least of my problems, okay? Just saying. Don't walk around your whole life that way, otherwise people will wonder about you. But I'm just saying, for a physics test, it's fine. All right, so I'm going to take a pause on the video for a minute, and I want you guys to try this one. Just take a minute, talk with a friend, talk it out. The first one is just a 3D diagram of what the setup is, and then I want you to look at diagrams B, C, and D, and look at the instructions. Instruction B says you're going to move this wire in the direction of vector A, so up and down. This diagram here says we're going to move the wire in the direction of vector B, so in and out of the page. I'm just helping people that are 3-dimensionally challenged, okay? And then this instruction here says we're going to move it in direction C, so to the left and to the right. So I hate to say that I'm going to leave a little bit of a dead air time on a video, but I'm going to leave a little dead air time on a video because I don't think that the take-up of this deserves its own separate video. But you guys take 10 seconds and I'll just ramble on and talk about how much I love the smooth flavor of my coffee. Classically roasted Colombian. That was delicious. All right, are you guys ready for take-up? Let's see how this works, okay? If you're not ready, that's okay. It's happening anyway. It's going to happen to you. All right, so if I take this wire and I move it in the direction of B, you notice, I don't even know how to illustrate this on camera, but what if I go out like this and I say moving in direction B, let's let my pencil be the wire. If I move this pencil in and out, towards the camera, away, towards the camera, away, am I going to be pushing through magnetic field lines? You guys see that if I just push this wire in and out of the page, it would be like I'm flossing the field lines. You know, like people floss between their teeth. If I floss the field lines, am I going to encounter a change in magnetic field? No. Essentially, if I don't bump into new field lines in my motion, the field isn't changing around my conductor. I'm just flossing the field. Okay? Yep. What's that? Oh, I'm glad you mentioned that. Because in A, what I'm doing is taking my wire and not going in and out of the page, but I'm going up and down. What? The one you're on right now is like... Oh, you're so right. A, B, you're right. You called me on it. Hey.
I'm so sorry to interrupt. Do you happen to have like an old school like plug-in speaker sound type thing? The projector sound isn't working. It's not coming out of my actual laptop. copy.
I don't know. Let's take this up in a second.